I can't be with you today, but I've left you this video lecture because the topic that we need to cover today is something we just can't skip. In some ways, it's the keystone for the entire course. It's the place where fields, electric and magnetic fields, meet space-time, the principles of special relativity. Okay, so let's begin. So let's start by thinking about a uniform electric field in space. The field is produced perhaps by a couple of parallel plates containing uniform surface charge density sigma. And if we arrange the plates perpendicular to the x-axis, then the field that's produced will be in the x direction. And the magnitude of that field will be sigma, the charge density, over epsilon naught. What does this situation look like to an observer that is moving in the x direction at a speed v? What field does that observer see? Well, the answer is that that observer actually sees a field that's pretty much the same. Although the two plates appear to be closer together, they still have the same charge density because the sizes of the plates, perpendicular to that direction of motion, are unchanged. And so with the same surface charge density, we get the same electric field between the plates. The x component of the electric field looks no different to the observer that is moving in the x direction. But what if the field is actually in the y direction? We might arrange that by a couple of plates that are horizontal plates. They're perpendicular to the y-axis, and they have a uniform distribution of charge, sigma and minus sigma. Okay, so that's the situation. That's how we've arranged to have this uniform distribution of this uniform field in between the plates. What happens if we now look at it from the point of view of our observer who's moving in the y direction? Well, of course, now when the observer looks at the plates, they are moving. And because they are moving, they undergo length contraction. So the same total charge on the plates occupies a smaller area, an area that's smaller by the factor gamma. And so that means that the charge density on the plates goes up by the factor gamma. And therefore, the electric field in the y direction between the plates goes up by the factor gamma. So the same thing would be true, of course, of a z component of electric field. So what's the lesson here? The lesson is that the electric field, the field that is experienced by the observer, depends on the frame of reference of the observer. Okay, let's consider a related example. The question is, how does the charge density in a region of space depend on the frame of reference in which you examine it? So what we imagine is a charged fluid, and it has a charge density rho. Now, if the fluid were at rest, if we look at the frame of reference in which the fluid is at rest, then that is what we might call the proper charge density, rho naught. And so the total charge in a little box, a little volume, would be dq equal to rho naught dv, dv being the volume. But if we look at this same little volume of charged fluid in a different frame of reference in which the fluid is moving, then that little volume will be length contracted. So its volume will go down. The new volume will be just dv naught over gamma. But it contains the same amount of charge. So that means that the charge density must be greater by a factor of gamma. So this is really interesting. Everybody will agree on what the charge density of the fluid would be in its reference frame. Everybody agrees on the proper charge density, rho naught, of the fluid. But in the frame of reference in which the fluid is moving at a speed v, then the charge density is rho equal to gamma rho naught. gamma times the proper charge density. So the question is, where the heck does that gamma come from? The answer is fascinating. Let's define a new 4 vector. And the 4 vector is just the product of the proper charge density and the 4 velocity of the fluid. And that's called the current 4 vector. And so it's rho naught times u, which means it's rho naught times the 4 vector whose components are gamma c for the time part of the 4 velocity, and gamma v for the space part of the 4 velocity. And when we multiply that out, gamma times rho naught is just equal to rho, the charge density in the frame of reference in which the fluid is moving. And so we have a 4 vector whose time component is rho times c, and whose space part is rho times v. But we know what rho times v is. Rho times v is just the current density. So we get a remarkable conclusion. The remarkable conclusion is that the charge density and the current density are just the time and space parts of a single 4 vector that describes how charge moves through spacetime. Let's see how this works out for a current flowing through a wire. Now the wire has 2 charged fluids. The first one is just the charged fluid produced by the atomic nuclei, and that charged fluid is at rest with the wire. So the current 4 vector for that is just the total positive charge density in the wire, that's the time part, and 0 for the space part. Now we imagine the charged fluid of the electrons, and they're moving. Let's suppose they're moving to the left, which means that the current density is to the right. Now the electrons have exactly the opposite charge density, minus rho c, but the space part, the current density is just minus rho times VE. That minus sign because, of course, the charge density of the electrons is negative. And so the overall current density for the electrons is minus rho c and J. Now if we put them together, we add them together to get the total current 4 vector for the wire, we find that the time parts, the charge densities, cancel out. The wire is uncharged when you can combine the nuclei and the electrons, but there's left over some spatial component, which is the current flow along the wire. So there's 0 net charge density, but there's a net current flow along the wire. Let's see what this looks like in space-time. So we imagine the positive charges, the nuclei in the wire, as a whole collection of world lines that are vertical in our space-time diagram because the nuclei are at rest. And the charge, the current 4 vector for those nuclei, the thing that describes the flow of charge, is a time-like 4 vector that points toward the future because the nuclei are positively charged. The electrons are a bunch of world lines that are sort of tilted a little bit over to the left because the electrons are moving to the left. But the current 4 vector points down and to the right. That is to say, it points to the past and a bit to the right because it points in the opposite direction of the 4 velocities of the electrons because the electrons are negatively charged. Okay, so what happens when we put these 2 things together? And the answer is that when we put these 2 things together, the time components of these 4 vectors cancel out, and what's left over is a little bitty vector. It's a space-like vector. It points entirely in the spatial direction, and it points toward the right, which is the direction of the current density in the wire. So that's how 2 time-like current 4 vectors can add up to a single space-like current 4 vector. So we have this wire, we've got a net current density flowing to the right. What does that look like to an observer who is also moving to the right parallel to the wire? What does this wire look like to this moving bystander? Well, of course, we're going to use our favorite trick. We're going to say that the time component of the current 4 vector, as seen by the observer, will just be given by 1 over c times the star product of the 4 velocity of the observer and the current 4 vector. So it's our usual idea of getting the time component as seen by the observer by just taking a star product with the observer's own 4 velocity. And the observer's 4 velocity is gamma c, that's the time part, and gamma v x hat. He's moving in the x direction at a speed v. And the current, the total current 4 vector is got a 0 in the time part and j x hat in the space part. And when I take that star product, I take the product of the time components and the dot product of the space components is subtracted from that, and what I get is a current, the current 4 vector in the observer's frame has a time component. In fact, it has a negative time component. The charge density, according to the observer, is negative gamma v times j over c squared. And this is weird, but it's true. The moving observer sees a wire with a net negative charge density. How in the world could that be true? Well, it works like this. So let's think of the wire as a pair of line charges, just a row of charges, positive charges at rest and negative charges, which are moving to the left. Now, both these lines of charge have the individual charges separated by a small distance s. It could be sort of the distance between adjacent atoms in the wire. So what happens when we look at this same arrangement of charges in a different frame of reference? As seen by the moving observer, the positive charges are, of course, closer together because of length contraction. They're closer together by the factor gamma, because S, that separation between the charges, is the proper length between the proper length of the space between two atoms, and so it's we just divide it by gamma to get the spacing there. But the spacing between the negative charges is not quite the same, because S is not the proper length. The electrons are not at rest in our original frame. The proper length is something different. And gamma is not quite the right factor because we're moving, because we're not comparing to the rest frame of the line of electrons. And so the net result is the two separations of the positive and negative charges don't wind up the same. The separation of the negative charges is a little bit smaller, and the net result is that the two sets of charges no longer exactly cancel out in a finite length of the wire. Let's draw this idea in space-time. So I've got a bunch of in my space-time diagram, I've got a bunch of vertical blue world lines representing the positive charges, and a bunch of slanted but parallel red lines representing the negative charges. Now, if we consider a moment of time, an instant of time, that's just a horizontal slice across my space-time diagram. That's where the time coordinate ct is equal to a constant. And if I mark where all the positive and negative charges are at that moment of time, then I'll find out that the positive and the negative charges are equally distributed along that line. So in this frame of reference, the frame of reference, the rest frame of the wire, of the nuclei, then in this frame of reference, the positive and negative charges are equally distributed. There's no net charge on the wire. But in a different frame of reference, my axes will point in different directions. And as we've seen, it's a little bit surprising. In a frame of reference of somebody moving to the right, the CT axis is tilted to the right, but the X prime axis is actually tilted up. They appear to be at a less than 90-degree angle in my space-time diagram, but that's just because my space-time geometry is not quite the same as the geometry of my diagram. So I've seen this before. So in order to look at a moment of time in this diagram, I have to draw a slanted line. That's a moment of time in this frame of reference. Well, where are the charges? Well, if we look, the positive charges and the negative charges are where the various world lines intersect this slice, and we find out that the negative charges are actually a bit closer together. You see on the left-hand side of the diagram, the positive and negative charges are nearly coincident. But on the right-hand side of the diagram, as we move over to the right-hand side of the diagram, the negative charges are more closely spaced than the positive charges. And so that means that in this frame of reference, that same set of charges will appear to have more negative charges per unit length than positive charges per unit length. It will have a net negative charge density. So what does all this mean? Well, let's imagine that our observer is carrying along with him a little positive test charge, and we'll see what happens to the test charge due to the effects that we've produced. Well, so because there in the observer's frame there's a negative charge density on the wire, that means that there will be a net electric field pointing toward the wire in our diagram. So if lambda prime is the charge per unit length, which is the charge density rho prime times the cross-sectional area A, that's just going to be minus gamma V J times A over C squared. So now let's see what the electric field will be. Of course, the electric field due to a linear charge density lambda prime, this is now the electric field that the observer sees. The electric field will be lambda prime over 2 pi epsilon naught times R. And that will be now minus gamma times V times I, the current in the wire. Why? Because that's just J times A, the current density times the cross-sectional area of the wire, over 2 pi epsilon naught times C squared times R. And that means that there's going to be a force acting on the charge. The force, which is going to be the test charge Q times the electric field that it sees, the field seen by that moving observer. And so that's minus gamma times Q times V times I over 2 pi epsilon naught C squared times R. What is this mysterious force? Well, to keep things simple, let's imagine that the observer is not moving very fast, and so gamma is about equal to 1. So we'll just ignore gamma in our expression. So we have a charge moving at a speed v along a current-carrying wire, experiencing a force which is Q times V times an expression in parentheses which depends on where you are, but not what your charge is and how fast you're moving. I over 2 pi epsilon naught C squared times R. And this is a very mysterious force. What are the characteristics of this force? Well, first of all, the force points toward the wire because the moving observer sees the wire as having a net negative charge. So the positive test charge is pulled toward the wire. And the second thing is that the force depends on the velocity of the particle, but it's perpendicular to the velocity of the particle. And the third point is that the force depends on something we could call the B field, which is that thing in parentheses, the I over 2 pi epsilon naught C squared times R. And this depends on the current carried by the wire and how far away from the wire we are. In fact, we can write down an expression for the B field. We can write it down as mu naught over 2 pi times I over r, where mu naught is a new constant that we define to be 1 over epsilon naught times c squared. And of course, you see what I'm saying. In fact, this B field is exactly the magnetic field due to the current in the wire. This is such an astonishing conclusion that we have to pause a little bit and take stock. What we did is we began with two ideas: the idea of the electric field produced by charges, and the idea of special relativity, the idea that all of physics takes place within space-time. Now, we first noted that the components of the electric field are different in different frames of reference. And then we found out, what's even more surprising, is that charge density and current density are actually parts of a single current 4-vector. The charge density is the time part, and the current density is the space part. Now, a wire with no net electric charge, but an electric current in one frame of reference, can have a non-zero electric charge density in another reference frame. And because of that, a moving charge near a wire will experience a velocity-dependent force related to what we call the magnetic field near the wire. And that magnetic field, we got an expression for it. It's mu naught over 2 pi times the current over the distance to the wire. And that mu naught is defined to be 1 over epsilon naught times c squared. What is this new magnetic field? It's very simple. A magnetic field in one frame of reference, the frame of reference of the wire, appears as an electric field in the frame of reference of the charge. The charge feels an electric field due to the net negative charge density of the wire. So let's review what we know about magnetic forces and fields. We know that a charge moving through electric and magnetic fields experiences a force, the Lorentz force on the charge Q, and that force is Q times the local electric field plus Q times the velocity of the charge cross the magnetic field. The magnetic force involves a cross product between the velocity and the magnetic field, and we know how to figure out the direction of that cross product by the right-hand rule. In any case, that force is perpendicular to both the direction of the velocity and the direction of the magnetic field. And when we have a wire carrying current, the electric field actually, if we visualize it by field lines, the electric field lines are circles around the current carrying wire. The direction of the magnetic field is actually, in the location of this test charge in our diagram, is actually pointing out of the screen toward you. And so that's why the positive charge moving to the right experiences a net force downward. It also means that if we have a whole bunch of positive charges in a wire, let's say, moving to the right next to the other wire, that wire will be attracted toward it. So in fact, if we have parallel currents, two wires that are running parallel, carrying electric currents in the same direction, then those wires will attract each other by this magnetic force. And if the currents are flowing in opposite directions, the force between the wires will be in the opposite way. The wires will repel each other. This is a fantastic idea, one of the most astonishing ideas in the whole history of physics. If we knew nothing about magnetic fields, we just knew about electric fields, but we also knew the laws of space-time and special relativity, we would be able to predict the existence of magnetic fields on that basis alone. electric and magnetic fields are not unrelated to each other. They're part and parcel of the same thing. The single electromagnetic field, of which electric and magnetic fields are different parts, just like energy and momentum are different parts of a single momentum, energy momentum 4 vector. Okay, so there's still a lot that we'll need to understand about magnetic fields and about the whole rest of the subject. For example, we need to have a lot more detail about how magnetic fields affect moving charges and currents. And we also need to know exactly how do currents produce magnetic fields. We need to know what the fields are due to long straight wires and sheets of currents and loops and coils and so on. We need to know a lot about how different arrangements of current generate magnetic fields. But we also need to go deeper. We need to describe the general laws, the field equations that govern both electric and magnetic fields and connect electric and magnetic fields together. And we also need to know more about other magnetic phenomena, like, for instance, what does all this have to do with actual magnets, the most familiar example of magnetic forces? What do magnets have to do with currents and moving charges? And in all this, what we're going to seek is a deeper understanding of the relationship between electric and magnetic fields. So, that's all for today. You have some exercises to work on. I'd like you to work those exercises and turn them in at the beginning of our next class. And I'll see you when I get back. Good luck.